Hello, and welcome back to Macrobiology. We've been talking about communication, and today I want to talk about specifically communicating fitness. And when we ask ourselves what fitness is, we can say that it is the organism's success in passing genes to the next generation. Okay, so here's a little quiz question. First of all, which statement describes a swallow that has the greatest evolutionary fitness? You have a swallow that lives to be 3 years old, has 4 offspring, 2 of those reproduce. One that's 5 has 5 offspring, 1 reproduces. Swallow that's 2 has 4 offspring, all reproduce, and a swallow who's 7 who has 3 offspring, all which survive to reproduce, or they're all equally fit. Well, I'm going to tell you right now, they're not all equally fit because it's really only about how many genes you pass on, right? And age is not important either, right? So you have this one who's 7 and has 3 offspring. Well, that's only 3. So here you have 2 offspring, here you have 1, here you have 4, and here you have 3. So the one that has 4, even though they're only 2 years old, has the highest evolutionary fitness. Okay, so we're going to talk about 2 things today. We're going to talk about visual communication, and we're going to talk about auditory communication. And we're going to focus on those. And visual communication, just as a little review, is most effective over short distances. It's almost instantaneous, okay? Now, there are problems if you have something blocking the way or if it's dark. So this is really a diurnal thing, a daytime thing, and we are predominantly visual and we are diurnal, so there you go. Now, there are 2 types of visual communication signals. There are active signals and there are passive signals. And active signals are when you have a posture or a movement that conveys a message. And by the way, visual communication can actually convey quite a lot of information, unlike chemical communication, for example. But the example that I want to use, here's one where telling a dog to stay. And so this is a cross-species visual communication, which happens all the time. And here's a threat display in an owl. An owl is telling some sort of, other predator that it's here, or maybe another owl even, that it's huge, don't mess with it. But this is not what the owl looks like most of the time, and so that's why it's active, it's a posture. Now, facial expression is something that I want to highlight because here's a cute expression, and this photo is courtesy of Elizabeth F. And lots of animals do this. They will make large gestures that will convey a very simple message. But when you start moving into the apes, specifically the great apes, you start to see emotion, like real emotion expressed through the face. And it turns out that this is such an important part of our communication, especially for women. Women are like face reading machines. And sometimes that doesn't always work out because sometimes we don't interpret properly, but you can see, this is kind of a, what's going on here expression, and here we have a nice contented expression, and this is like, things are going okay, maybe a little nervous perhaps, and then this, angry, determined, whatever, but we see these and instantly recognize the message that goes with it. Okay, now passive signals are really about the animal itself, right? There's some character of the animal, and it's going to be size, shape, or color that's going to convey information. And here you have a poison dart frog, like a nice little poisonous frog. Here you have the beautiful coloration, and remember, birds use their coloration to show how healthy they are, how fit they are, how many resources they have, how dominant they are. Whereas this guy's saying I'm poisonous. All right, and then the mandrill, here you have other sexual selection features, and so you have this bright red stripe in the middle of these blue kind of panels on either side of the nose, and then of course they have the multicolored hind region. But the other thing is you can use these passive signals in an active display, and so a lot of times a passive signal and an active signal are combined to give a more powerful signal. And here, when you look at this mandrill, you can see he's got his mouth open with these giant teeth. That is really, really threatening. And the color helps enhance that, and it draws the attention to those very large teeth. And so there's twofold. You have the sexually selective component of the bright colors, but then you also have the bright colors as an arrow pointing towards weapons. Now, you can also see this in the peacock, right? Because you have these beautiful peahens, love, symmetrical tails, all this good stuff, and the peacocks raise them up to actively display them so they can be seen. Okay, and here's a bird of paradise doing the same thing. And the anoles that we have around here, this is actually not one of our anoles, but ours are cute and little green and have the solid colored dew flap. But anyway, they'll throw this out. So you've got that passive coloration with the active movement of it. Okay. Now, displays are really important, right? And so when you take this, perhaps some passive and active, and you put it together, and then you make this complex ritualized display, it can actually convey a whole lot. If you get the steps right, then you're a good choice. If you don't, maybe you're not. And most often this is used for courtship. And really most often it's used in birds. Birds are the dancers of the animal kingdom. Okay, now there's something else that eyes can tell you that's really important. Eye placement will tell you whether an animal, most of the time, whether an animal is an herbivore or a carnivore. And so when we look at herbivores, for the most part, you can see that they have monocular vision, right? Because their eyes are placed on either side of their faces. So they can see all around them except directly behind them. And this is so they have a good range to see predators. Now, these guys, though, have totally forward-facing eyes. Okay, this means that they are carnivores or omnivores in some cases, but that they eat meat or insects or something because they need the depth perception to know where their target is exactly, and so they have the binocular vision, and we also have binocular vision and and that is because we are predators too. Okay, now, when we are talking about seeing, we typically think about just the visible light because that's what we see, but lots of animals actually sense other wavelengths. Okay, light has a really high energy, and so it allows for really good location and resolution understanding of where targets are, but it depends on actually what you're sensing as to how complex a picture you get. Obviously, the more wavelengths that you can sense, the more rich the picture is. And like I said, we only do visible light, but lots of other animals do ultraviolet and infrared as well. And so when we're talking about acuity, we're talking about the ability to distinguish different subtle differences in the light. Okay, now some animals actually have polarized lenses, and large birds of prey, including the bald eagle, have lenses. Their actual eye will cut glare, just like polarizing sunglasses, because they only allow in the same direction of light waves, and so they can go fishing without getting the glare on them. And then some organisms actually sense infrared, right, like pit vipers. We do visible light, and I've already talked about this a little bit. And then UV, a lot of insects and some birds actually sense UV as well. They see UV, and so birds look totally different to each other than they do to us. Okay, now nocturnal vision is really important because if you're a hunter and you hunt at night, then you really need to be able to see. And I just want to say, as a side note, this is not a real picture. This is a false color image right here, but I like it because it shows it. This, on the other hand, is a real picture, as is this, as are those. And what you're seeing is the light from the camera reflected back off of the retina of these animals. And cats and some primates have what are called a tapetum lucidum, what is called a tapetum lucidum, in the back of each eye, and it is a highly reflective surface. And so when these animals get the image, right, there's a lot more reflection going on in the back of their eyes, and so they actually see almost as well at night as they do in the day because they maximize the amount of light that's coming in. And speaking of light that's coming in, you have light bouncing off of an object. It goes through the cornea, at which point this is the first lens it goes through, and then it is focused, right, in this lens, which is actually the lens of your eye as it goes through the iris, and the iris determines how much light will be let through. And then the image is actually inverted because of the combination of these two lenses, and it's projected onto the retina. where all of the photoreceptor cells are. And the photoreceptor cells in our eyes come in two big categories, rods and cones, and rods and cones. Rods sense light and dark, and then cones come in three colors, red, green, and blue, and that's what allows us to see color. And then they are all those signals hitting those photoreceptors are funneled to the brain through the optic nerve. There's a little bit about vision. Okay, now auditory communication, communication by sound, okay, is effective over longer distances because visual signal you have to actually be able to get the light to come all the way to you, whereas sound with no obstacles, sound will travel through things and it travels farther. It's also almost instantaneous, and it works really well in the dark, obviously, in dense forest, but not too dense, because if it's too dense it's going to block the sound, and in murky water because sound travels really well through water. I think something like 4 times faster through water than air, and that's because sound is a different kind of wave, and so the fluidity of the water really helps that propagate those waves. Okay, and this can convey lots and lots of information. I mean, think about us. We also are auditory in that we talk, right? And so we get a lot of our information from talking to each other. And so we do all kinds of things ourselves, but then there's lots of sound in nature. And one of the things that's actually pretty cool is a male water strider will actually sit and vibrate its legs, sending vibrations through the water that attracts mates. This is not actually sound, but it is the use of waves to communicate, and I like that. Now, male elks bugle to attract females and to defend their territories, and they let out this huge trumpeting sound that can be heard really long distances. So here we're in the sound. And then ultrasonic, it doesn't just have to be sound waves that we can hear. Lots of animals communicate with infrasonic waves and ultrasonic waves. The whistling moth is one of those, and we can't actually hear it, but it's making this clicky type noise because it rubs its wings together and it has these hard structures on them that tap together. So all kinds of sound. Songbirds, really complex patterns and things like that. Now, how do we sense sound? Sounds, like I said, are pressure waves, right? They're created by movement, and so in order to make a sound, you have to have something that moves. We have vocal cords that vibrate. That's how we do it. The rattlesnake has the rattle that it hits back and forth. And so the little rattles inside hit the walls, which cause vibrations. And so we have to have some mechanism to make the sound, but then we also have to have a mechanism to receive the sound, and that is something, right? And we're most familiar with ears, and so that's what we're going to talk about. 2 ears are better than 1 ear because, again, that allows us to triangulate where the sound is coming from, and asymmetrical shapes actually seem to help figure out where the sound is coming from a whole lot better than just having 2 identical ears. And if you'll notice, this little owl has one that's kind of up and one that's kind of to the side, and owls can turn their heads almost all the way around, and so they get a really good sense of where things are. They can hear extremely well. Okay, so other examples of using sound. Whales communicate over really long distances using really low frequency sounds because the lower the frequency the sound, the farther it's going to travel intact. And then bats see with sound. They echolocate. And so what they do is they will actually send little sound waves that bounce off of something. They receive the sound wave back and they interpret that into a picture, right? And so anything that echolocates, bats and dolphins, they see with sound, and I think that's kind of interesting too. Okay, and then how does hearing work? Well, you have your ear. The pinna focuses the sound into the ear canal, right, which vibrates the tympanic membrane, which we know better as the eardrum. When that happens, these 3 little bones here, they're sometimes called the hammer and anvil, the incus, the malleus, and the staples, they're going to vibrate, and they're going to vibrate the cochlea. Okay, and then the cochlear nerve is going to pick up those vibrations, and then here you have the semicircular canals, and these are for balance. Okay, these help your brain know exactly what's going on with where you are in space, and so that's a little bit about hearing. There are also little hairs in here in the cochlea called basal hairs, and those hairs vibrate with the vibrations of this, and each hair senses a different wavelength of sound, and that's what's actually taken to your brain. So from the eardrum out, that's your outer ear, the eardrum and the three little bones here, smallest bones in your body, by the way, are the middle ear, and then the semicircular canals and the cochlea and the cochlear nerve are going to be the inner ear. Okay, that is it for our conversation about communicating fitness. And if you have any questions, please let me know, and I will see you next time. Thanks for listening.